the next speaker will be in person, Adam Labdon, and he will talk about the inner disk view of episodic accretion. I think your presentation is uploaded here. It's there.
Hello? No. Yes, okay. Yes, hello. Thank you for the opportunity to talk. Yeah, I'm going to be talking about the interferometric view of episodic accretion disks. When I say interferometric, I mean optical interferometric. So we're looking at the very, very inner regions of these objects. Just to show this plot, to remind everybody, when we talk about interferometry, we're looking at near and mid-infrared. So we're looking at the very inner regions around the sublimation rim, processes interior to this, and then the very few inner AU of the disk as well. Whereas most studies, of course, focus on the further out disk with ALMA, with imaging, with other things. This is very difficult to do. We rely on, well, we need brighter objects to do optical interferometry, so we're limited with our sample. But there's a few objects that we've been able to observe with both VLTI or with the northern equivalent in Parra. And I'm going to present a few of those here today. So the project was born out of, there was some, quite a lot of unpublished data in the ESO archive from the VLTI of amber, MIDI, and also got some new data with gravity on a few different FURI objects. And because these are hard to observe with optical interferometry, it's valuable data to get out there. We don't know quite what the inner disk of these look like in most cases. So I thought I'd look at this, and we've got quite a wide wavelength coverage, as we'll see in a second, so we can explore different scales of the disk. And importantly, with the different wavelength coverage, we can explore the temperatures across the disk as well, and possibly look at things like how the disk is being heated as well. So the 4 targets that I include in this talk, of course, it started with FURI itself. It was a PhD project of mine back a few years ago. So this one's already published. We had JHK interferometry. The other 3, or the next 2, V88 FURI, V646 PUP, are also high accretors. We had near and mid-infrared objects, interferometry. We're not quite sure about when the outburst happened, but they're still at the high accretion state. They're still in the outbursting phase. And then there's this other strange object, Bianori, which some people describe as FUR-like. It's got some of the spectral characteristics, but it's got a low accretion rate. So maybe it's post-outburst, maybe there's something else going on, but it's something that we had data on anyway, with gravity data, but just in the K-band in this case. Yeah, well, we all know, so just a bit of motivation. We're looking at this to explore, well, the effects on planet formation is the ideal. So obviously FUR outbursts change the disk fundamentally, and will change how planets form. But we can move on to the actual observations and the data. So the first object I published back in 2021, this was FURINS itself. We had its northern object, so we had Chara data in the J, H, and K band. So it's the first J-band interferometry going down to spatial resolutions of 0.35 milliarc seconds. So very, very high spatial resolution. And what we're able to do with our multi-wavelength interferometry is to fit both the photometry and the spatial data simultaneously to look at how the temperature is changing across the inner disk. We basically build up a model of concentric rings. We give each ring a temperature and a brightness, and that way we build up the brightness profile and the temperature profile that we're observing across the disk as well. And what we find is something that looks a little like this. So we see no evidence of an inner gap, whether that's due to the lack of spatial resolution, even with 0.35 milliarc seconds. So we see continuum emission all the way down. We have, yeah, so we put this down to indicative of boundary layer accretion rather than some magnetospheric accretion. We also model the temperature gradient using this concentric ring model that I mentioned. And we find it's got a pretty steep temperature gradient. If you look at some old models based on, or that were originally developed for black hole accretion disks, you can try and infer some information about what that temperature gradient means in terms of how the disk is being heated. If a disk is being passively heated by the star alone, like in a classical Herbig type or T-Tauri type scenario, then you'll have a much shallower accretion disk with a T proportional to R of the power 0.5-ish or minus 0.5. But if you have viscous heating within the disk, as you would expect for these FURINS, very turbulent, very viscously heated disks, you have a steeper temperature gradient. And this matched with what we found for F Uranus. We found a very steep temperature gradient. There's got some additional heating within the inner disk. Yeah. The next object that we looked at was V883 Ori. This has the wonderful ALMA images. And yeah, so this was looked at with mostly archival data. We had a lot of AMBER and MIDI data. So AMBER is an old K-band, MIDI was the old N-band instrument, and we also got some new gravity data on this instrument as well. And what we find is something not too dissimilar to F-Uri. We find a fairly steep temperature gradient, not quite as steep, but we also see a slight inner gap, which is within what you might expect for the classical sublimation radius, but there is a gap that we detect more or less within the object. It's at the limit of what we can resolve, but we do detect some sort of gap in there. The other interesting thing is that we have some closure phase signals. So for those who don't know optical interferometry, closure phase signal means you have some asymmetry, something is not circularly symmetric within the disk. It seems to be that we might have a tentative companion detection. Well, you can't see it so well, but there's a central disk here, and then out here there's some extra bit of flux contributing at like 5 milliarcsecond separation. Whether this is like a companion or whether it's a blob of material within the inner disk is still something we're working on. We have many epochs of data and they show slightly varying things, so it's still a bit of work in progress, but there is some asymmetric blob type thing within the inner disk. Yeah, the inner disk also matches in inclination, position angle well with the outer disk, so we don't have any skewed things going on. We also see there's a large amount of unresolved flux. It's like halo flux, as we tend to call it. This is just unresolved flux, background flux, if you like. We don't resolve at all with the interferometry. V646 Puppis. This is AMBER and MIDI data again. I've also included some Matisse data that we've managed to get our hands on. Yeah, this is the last of the higher accretors. And this one looks very, very similar to F Uranus. We don't see any evidence of any gap, and we have the very steep temperature gradient again. So it seems to once again be viscously heated in a very similar manner to F Uranus. They seem to show the same kind of things going on there. And the last one was this strange object, this BN Orionis object. This was just based on gravity data. This came about because I was looking at lists of potential F-Uri-like objects, and this one came up. It was technically observable, but nobody had ever observed it with VLTI or with interferometry before. Maybe it had an outburst, and maybe it's now in post-outburst state because it's got a very moderate accretion rate, 10 to the minus 8. But the disk doesn't really look like the others at all. It has a very large inner gap, much larger than you'd expect from either magnetic truncation or sublimation or any of those other processes. So the inner disk has been cleared somehow. It's in a transitional stage maybe, so was it cleared maybe by the outburst, or was it cleared by a companion sculpted by a planet or some other process? We don't know, but we see it's quite heavily inclined, which is why it has this strange brightness distribution. This is just the inclination effect. This is the far side of the disk, which is brighter because it's exposed to us. The near side is kind of shadowed by itself. Yeah. It also has a very shallow temperature gradient, as you might expect for a disk with a large inner gap. It starts sort of colder, and then the temperature gradient is very shallow as you move out with radius. So it seems to be a very passively heated, very normal transition disk-like thing, but with a FUR-like spectrum. So we're not quite sure how to classify this at the moment. Yeah, so well, this is the temperature gradient that we see. As you see, it's got a much larger inner gap. It starts fairly cold at about 1,000 Kelvin and has a very passively heated temperature gradient. So yeah, if anyone has any ideas about how to classify this, I am open to them. So yeah, just to summarize very briefly what's going on here. There's obviously a lot more we can tell from these results. We can look at how these disks are being heated and look at viscosity and things, which is what we're doing at the moment. The key thing to remember about looking at these temperature gradients and assigning temperatures to different radii is that this is the observed temperature, and the thing you're observing will change with wavelength. So in the K-band, you're looking at very much the surface level of the disk, the very top outer layers. As you go to longer wavelengths, you get very slightly deeper. And so, yeah, saying temperature gradient it's the observed temperature gradient, not a physical at a set layer of the disk. Yeah. So that brings me, well, that's the end of my results to present. Just to say that, as I mentioned, we don't have many objects going forwards, but this thing coming to VLTI is Gravity Plus, and this is not just a gravity upgrade, this is a VLTI system upgrade. So I mentioned at the beginning, the problem with FURs is they're very red objects, and the problem that we have at the VLT is that you need to be able to guide and do your adaptive optics in the visible, which makes most of these objects impossible to observe. Gravity Plus is installing laser guide stars on all 4 of the UTs, which will then be used for the guiding and the adaptive optics of the telescopes. And so you can completely bypass the visible limit, and all you care about is how bright they are in the K-band, which opens up a lot more objects to be able to observe. So by the end of next year, when all of these are online, we'll be able to go to many more objects that we can observe with a VLTI, and we can really look at, from looking at maybe 6 or 7 objects in total, to looking at many, many more of these objects as well. So, and also there's many EXORs and other variable accretors that light the limits. So that brings me to the end. Thank you.
Thank you very much, Aaron. Yes, questions? I think maybe we can use this one. Maybe you can answer.
So in the standard steady disk model with the zero torque inner boundary, it's not a power law all the way up to the exact inner edge. There's a peak temperature and it turns over. And I wonder if you've thought about modeling, assume that that's the kind of shape and whether it would affect your inner disk radius, for example, for V833.
It might, yeah. It might. I don't think it would affect our models too much because we're lacking, even though we have very high spatial resolution, it's not that high that would get to that point where we're seeing the turnover. So our spatial information is limiting at those very, very small radii is the problem. So.
It looks like we have a lot of questions. Is there any other microphone around? Okay.
Yeah, thank you for very nice work. And sorry if this question is mean, but you show some images, and so are these unique solutions to explain your observations, or are these still model independent?
These are very much model images. We have sparse UV data, so we can't attempt image reconstruction with this data. So these are model images, very much, yes. But they're the best fit model images that we have.
Over here.
Okay, thank you for a nice talk. So could you go back to the slide of V883 only? Yeah, that's right. So, sorry, I couldn't fully understand the constraining the location of the companions. So could you elaborate how did you constrain this location of the companions by using the closure phase?
Yes, so it is model fitting at this point. So, well, yeah, when we're fitting the companions, or the companion, yeah, this plot's a little misleading. But yeah, so this is not doing the temperature gradient modeling that I said before. This is kind of more standard modeling of, so you basically build up with different components. Within this model, there are 3 components. There is 2 point sources, one in the center, one out here, and then a Gaussian structure. And it's, yeah, fitting all of those simultaneously to both the visibilities and the closure phases. The Gaussian and the central point source will not impact the closure phases at all, unless you skew, unless you skew somehow, like with some azimuthal variation or something, the Gaussian, it won't impact the closure phases at all. So the only thing affecting the closure phases is the position of the companion and the brightness of the companion. So that is how we fit the companion. And we have multiple epochs with multiple closure phase measurements.
A last question from the back.
Thanks, Aaron, for this talk. I have a question about the gravity plus. Can you show us more details about how faint the target we can select for gravity plus? And also, since we want to, resolve this object, so it's better that they're closer to us, right?
Yes, better closer. In some cases, if the disks are too big, you can over-resolve them, which is a separate problem. But yeah, closer is generally better. For Gravity Plus, there's been a slight improvement in the sensitivity of gravity with some of the things. You'll have a slight improvement again with the lasers, but it's just a little bit of the flux injection. So it's just, you maybe gain half a magnitude or so. The big thing that you do, though, is that you bypass the visible limits that you had. So you don't need a star to guide the telescopes. You don't need a star for the adaptive optics anymore. And that was the problem with FUORs, that they weren't bright enough to do the guiding, to do the adaptive optics. But you bypass that completely by having laser guide stars that do that all instead. So the near-infrared, mid-infrared limits won't change too much, maybe half a mag or so, but the visible limit, the telescope limit, will be eradicated.
Thanks.
Okay, so thank you very much. I think that's it. Let's thank all the speakers of the session. And now we have a break for lunch until